This is a video of football player Hulk, appropriately named, kicking a ball so hard that it pops. But even Hulk hasn't kicked a ball the fastest in football history. That record goes to Ronnie Heberson, whose shot travelled at 130.5 miles an hour. That's almost twice the sorts of speeds that rally car drivers go at. To put it another way, it'd take the ball only an hour and 45 minutes to go from New York to Boston. That's pretty fast, but what would happen if instead the ball travelled at the speed of light? Before we get to answering that question, we need to talk about plasma. You know all about solid, liquid, and gas being the first three fundamental states of matter. Plasma is the fourth. Plasma is hot. As you give an object more energy, it transitions from state to state, moving from solid to liquid to gas. But if you fire even more energy at an object in a gaseous state, you can literally knock some of its electrons away from its atomic nucleus, like playing subatomic curling. This process is called ionization and is what plasma is, a soup of particles whose electrons have been knocked away. Plasma might seem like an abstract thing, frequently used in science fiction movies, but if we were to run a lottery of the visible things in our universe, there's only a 1 in 10,000 chance that what we get wouldn't be plasma. 99.99% of things in the visible universe are made up of it. Stars and nebulas make up the vast majority. Our sun, for example, is, for practical purposes, almost 100% plasma. The incredible pressure caused by our sun's gravitational pull squeezes atoms together with such force as to cause them to merge and make a larger element. But the energy required to hold together this larger element is less than the amount of energy needed to hold together the same atoms used to create it. So it releases an enormous amount of energy, which the star uses to keep itself from collapsing under its own weight. The energy these fusion reactions release then ionize nearby particles, creating plasma that's more than 6,000 degrees hot. But that is not as hot as plasma can get. Down here on Earth, we see plasma all the time. Across the globe, it's estimated we see it between 50 and 100 times a second, and in America alone, 25 million times a year in the form of lightning. Lightning is the result of a sort of natural battery. In a thundercloud, the top half of the cloud is positively charged and the bottom half is negatively charged, thanks to the way that ice crystals pass electrons to each other as they move around the cloud. Because the bottom of the cloud is so negatively charged, it repels negative charges in the ground underneath it, leaving behind a positive patch of land that follows the storm. Since positive and negative energies attract each other, they desperately want to run toward one another. But the air in between the ground and the cloud acts as a sort of insulator, like the rubber around copper cables. Only when the voltage in the cloud reaches a certain threshold, which surpasses the insulating powers of the air, does this enormous discharge of electricity take place. This is what you see with lightning like this, where the charges move from the cloud to the ground like a fork. But in rare circumstances, like the one in this video, it can happen the other way round, creating a scene where we're under a canopy of clouds supported by a tree trunk of pure lightning. This is called ground to cloud lightning and happens when the charges are reversed. In some cases, lightning can come from the very top, positive end of the thundercloud. This type of lightning has been known to travel more than 10 miles away from the thundercloud it originated from, seemingly appearing out of thin air, and is also where we get the phrase bolt out of the blue from. The lightning that makes its way to the surface is 30,000 degrees hot, superheating the air in the conducting column, forming plasma. And because the air is heated to 30,000 degrees almost instantly, it's given so much energy as to expand so fast it creates a 9-meter shockwave. What you experience as thunder is literally the air moving out of the way of the plasma at such speeds that it creates a sonic boom. Right, now we're ready to talk about what would happen if a ball travelled at the speed of light. that ball would be travelling extremely fast. To it, everything would seem to stand still. Even air molecules, which usually vibrate at the rate of a few hundred miles an hour, would seem to stand still because, well, the ball is travelling 600 million miles an hour. Normally, as an object travels through the air molecules on the front of it slow it down as it travels through them. But the ball is travelling so fast that the air molecules don't really have that option. The ball would slam into them with such force that the air would fuse with the surface of the ball, not too dissimilar to the way the fusion reactions happen at the heart of our sun. Each one of these fusion reactions would release a burst of gamma rays. The gamma rays and high-energy particles emitted from the front of the ball would screech outward, knocking electrons away from the surrounding air molecules, turning it to plasma. This increasing bubble of lightning-like plasma would expand at the same speed as the ball, eviscerating everything in its path, including the person who kicked the ball. The sheer heat of these thermonuclear reactions at the front of the ball would disintegrate it, sending fragments of its surface off with such force that as they collide with more air molecules, they create more fusion reactions. By the time the ball reaches the goalkeeper, to him the striker hasn't even kicked the ball yet because the light from that event is travelling alongside the ball. By this point the ball would have almost fully disintegrated, but the bubble of plasma and debris will continue moving forward. Within the first microsecond of being kicked, the striker, goalkeeper, goalposts, the stadium and the surrounding neighbourhood would be vaporised. To onlookers, you would see nothing. Then instantaneously a blinding light like a lightning strike many times brighter than our sun, which would fade over a few seconds, revealing to you the crater that used to be the football pitch and the mushroom cloud rising above it. Shortly afterwards, the energy released by this penalty kick would push the air around it at such speeds as to create a blast wave, a supersonic pressure wave that would move, tearing trees out of the ground and obliterating houses in a mile radius. It wouldn't be like a nuclear explosion, really, because it is a nuclear explosion. A mushroom cloud would erupt from the surface, creating firestorms that would likely engulf the rest of the city. That, by most referee standards, I would assume, would be a foul. But what is not a foul is your company. Thank you so much for watching.